Now, suppose we have two and more heat conducting slabs in parallel. So, in parallel means I have suppose one rod here, another rod here. So, suppose I take two and this region has a temperature theta 1 and this region is maintained at theta 2. So, these are theta 1 greater. So, what happens? The heat current I 1 flows and the heat current I 2 flows through this rod. This rod has conductivity K 1, K 2, length L 1, L 2, area of cross section A 1, A 2. In place of writing all these things, I just write that the thermal resistance of this is R 1 and thermal resistance of this is R 2. Now, what I want, in place of these two, I want a single heat resistor which will also transport the same heat current, that is the sum of I 1 and I 2. So, I want my I is equal to I 1 plus I 2 if the same heat, same conditions, that is these two junctions, it again at theta 1 and theta 2 temperature. So, under the same temperature difference, heat must transfer I current, which is the sum of I 1 and I 2. Now, I will be equal to the theta 1 minus theta 2, the temperature difference by the thermal resistance. I 1 will be theta 1 minus theta 2 by its thermal resistance, and the heat current it passes is temperature difference by R 2. So, these two terms cancels out. So, this becomes, so this is the same way in which the parallel resistance in current conduction is added. So, thus the thermal resistors in parallel will give 1 by R equivalent is equal to 1 by R 1 plus 1 by R 2.